it's because you're not used to doing it this way.
So it says conical section of material extends over the range 2 centimeters to 9 centimeters.
All right, so we're going to be in cylindrical coordinates. And here's what it amounts to, I believe. You have two plates, and this is like A would be this radial distance, and this is B. And then these plates have a given height. Now it's not easy for me to do this in 3D, but this would be H. Just think of this, take two parallel plates and then put them on like a hinged area and open them. Y'all follow me on this? It looks like a hinge, a door hinge, if you can imagine that. So if you look down the side of it, it looks like this. And these things would have that length, and I'm not even sure how I could do this projection very well, but you can follow me on that. It's like it's flanged like this. So what I'm going to do is this.
It also says beta is between 0 and 30 degrees.
That's how open the angle is. Okay. This is a classic problem. This is something you probably got in physics if the teacher decided to go through some more difficult things. But here's what it looks like from the side. Just the side view, you're going to look right down the axis. If this is the hinge point, you have something inner radius A, outer radius B here. If this is the hinge point here, it goes straight out to B. So there are two plates, and they go in a distance, it's H. Y'all with me? So think of a door hinge, all right? Then there's an angle of separation here, and I guess he calls that phi1 or something like that. It's a given angle, it's set. Y'all follow me? It could be like 30 degrees. It doesn't matter at this point. You with me?
Yeah.
Now here's the thing they don't tell you, or he didn't tell you. If you had physics, depends on the instructor you had. But if you have two parallel plates, I'm going to draw it up here. You don't need to write this down. Just if you pay attention, you'll understand. All right, if you have two parallel plates that are separated by a very small distance, and there's a voltage difference between them. Say this is going to be plus V0 at the lower plate, and then 0 volts at the upper plate. With me? The field lines, the electric field lines, would go from the positive to the negative plate. Do y'all follow me on that? There would be no electric field along the direction the plates are in. Does that make sense to everybody? How many see this right here in your mind's eye? All right? Now, as this opens up, what would happen is this. Now the field lines do this. They become curvilinear, and there's an actual course you can take called conformal mapping, solving differential equations, where you actually map the geometry and take this, and you'll make it conformal to this geometry, so you can see things better. But I'm not going to even touch that. That's advanced. But y'all see what I'm saying here. All right. So if the field lines on this problem are going this way, and you're just going to have to take my word for it. They are, if this has a given voltage V0 and this is, say, 0 volts, then there is no radial electric field value. Y'all follow me on that? The field value is going to be in the A phi direction. Does that make sense to everybody, class? All right. There is no electric field or D field in this direction, nor into the board, because everything, you might say the cross section doesn't change. Into the board, this thing extends in and out of the board, and this is the one thing you have to appreciate. In truth, there will be fringing fields right at these points, all right? There will be electric fields where you will get electric field components that are radial, but they ignore those because they're minor. Sort of like when two giant parallel plates separated by a small distance, we ignore these effects at the edges. If we didn't, we couldn't solve any problems with reasonable accuracy. Do y'all follow me on that? Okay, so now getting back to this problem, how do you solve it? Well, I can almost use this geometry here, easier. Okay, we put a voltage here on the lower plate, call that V naught, ground the upper plate, but put 0 volts on it, okay? I know the angular spread here is some phi1. Now, based on the fact that the field lines themselves are only in the A phi direction, we go through and we use the Laplace equation, and then it's assumed that there is no charge density in between them, correct, class? In that problem?
It says epsilon relative is 9 and,
That's constant, right? Nothing, there is no rho that changes rho. There's no volume charge density in between the plates. That's my point. You all see that? All right, so now you can come over here and you can take the del squared equation. You can just set it equal to 0 because that equation is going to dictate the behavior between the plates. Not at the plate's surfaces where the interface is across it, but right between the plates. If you look in cylindrical coordinates at del squared operator, if you have your books, you can just look at the back of it, and you're going to see something like this. It'll be 1 over rho times d rho of rho dv d rho plus, and it's 1 over, I think, rho squared times second derivative of v with respect to phi plus, and then it's going to be second derivative of v with respect to z squared. All this is equal to 0. Take a look at your books. Do y'all follow that? In the very back of your book, on the back page, back cover, take a look in the back cover. It's called the Laplacian. It's a del squared operator. It'll be the last operator shown. Do you see it? All right, take a look. That's what it is, right? It's a scalar. Now, this is the important thing you notice. Here, remember I made a big point to say V does not change with radial distance. Do you all see that, class? So I can get rid of this term. dV d rho is 0. Do you all follow me? If it wasn't the case, it'd be a much more difficult problem. So that means I can get rid of this. And also it doesn't change with Z. Z would be into the board. There is no variance with Z. As a matter of fact, you can think of this as 2 infinitely long plates that have a finite hinge size. So this goes away. So now I'm down to there. And then after this point, it's just a matter of focusing. It becomes easy. Now remember, this is a little different because before when we did capacitance problems, what did we do? We assumed Q first, and then we got what? From Q we got D, from D we got E, from E we got V. This one's different, doesn't work that well. If you assume, that you can't make that claim about the charge density being constant across there because it isn't. You'll see why. So now I have this. Do you all agree we can multiply both sides by rho squared, right? So that just gets rid of it, right? Still 0. Now we integrate once. Integrate once, we get dv d phi is equal to some constant k1. And then when we integrate again, now we get v, that is a function of phi, would be k1 phi plus k2. I know this may seem a little odd to you, but this is really just a linear equation. But now, instead of having a dimension x, y, or z, the dimension is phi. Y'all follow me on that, guys? Okay, so this is the voltage equation. Now we have to solve for the constants. How do you always solve for the constants in any differential equation solution? Anyone? Everyone? Is this payback for something I've done? I mean, nobody at all? Come on. It's boundary values, right? I put boundary conditions on there, a V naught and a 0 for a reason, because we need that information. We need the voltage to get the capacitance. It was an assumption. So now I say what? Well, I know at phi equals 0, I had V naught is, so this is V naught, phi equals 0. Phi equals 0, the K1 times 0 is 0, it's equal to K2, right? Well, actually, let me do it this way. Because that way, I'm gonna do something a little bit to make it easy on myself. What I'm going to do is actually have this. I'll make this V naught so this equation will little easier, make this 0. Oh, and it doesn't really matter. So now, if I come up here, the general equation is V as a function of phi is K1 phi plus K2. Now when phi equals 0, 0 is equal to K1 times 0 plus K2, right? And you can make the argument that K2 is 0. And then you can say V of phi equals V naught at K1 times phi1. I think he uses phi1 to talk about how open that angle is. Is that right? He has to define that as a fixed value, phi1 or something. Theta 1? Theta? Does it? You'll see it doesn't matter as long as it's a constant. It's the angular difference between the two, 30 degrees, something like that. You with me? So this is a constant. V1 is constant. All right, that means K1 is equal to simply V naught over phi1. And he may use alpha. I know that I think about it. Did he use alpha?
Yes.
For the, okay, we'll use alpha. That's not a problem. Put alpha in here. Okay? And I didn't look at the solutions. I don't know how, well, I don't know how he goes about that. But once we have K, actually, they look at the solutions on this. If that's K1 there, now I can say that in general, V for any given angle is equal to V naught over alpha times phi, and that's it. Y'all with me? That's the voltage based on my assumption of the voltage at the lower plate was V naught, the upper plate was 0. Now, once I have the voltage, my next step is to get the E field. I'm going in reverse. Usually, you assume charge, get D, get E, get V. Here, I assume V, now I get E. With me on this? So E is equal to minus the gradient of the voltage. Now, if you look in your books, this is cylindrical coordinates. The gradient is what? Well, there's several terms to it, but the only one that's a function of only phi would be 1 over rho. This would be minus 1 over rho dV d phi, and it would be in the a phi direction. Look in your book, if you have it, and look at the back where it says gradient in cylindrical coordinates. You'll see 3 terms. There'll be dV dz. There'll be a a dV d rho times a rho, and there's going to be a 1 over rho dV d phi. You all see it, class? A phi. All right. The other 2 terms, dV dz is 0. It does not change versus position z. And dV d rho is 0. Remember I said, if you're at a given angle, the voltage doesn't change along that straight line out. So now I come down here, and I get this. So I say my E field will be equal to minus, and it's going to be 1 over rho here, and then dV d phi, well, if this is V, when I take a derivative with respect to phi, I just get V naught over alpha, A phi. Y'all good with that? Now I've got my A field. This one is not, I don't know, you don't feel real good about these kind of problems until you do several of them, because this is not normal geometries we've been talking about. Okay, now after that, I'm going to get D, right? How do I get D from E, anyone? Remember, epsilon's a constant. It's just epsilon E, isn't it, class? That's as simple. So I just take this, and I'm going to get D by multiplying it. And now I have I'm going to just leave it as epsilon. Epsilon over rho, and then it's going to be V naught over alpha, A phi. So now I have D. Now, the key thing is when you have D, if there is a perfect conducting surface, and even though I don't know if he stated that, but I think he did. If this is a perfect conductor, then D normal is the charge density. Do y'all remember me telling you that, guys? D normal to the surface is the charge density. So that means I can say that now rho S is simply going to be on the lower plate epsilon over rho times V naught over alpha. And you can put a minus sign here, but that's rho S on the lower plate. So again, I started at V, got E, got D. Now I have rho because this is D normal if there's a conducting plate. Is equal to rho S, and that's real important. Now once I have rho S, I need the charge, don't I? Because if I'm going to get capacitance, I have to get the charge. You'll notice that rho S is a function of what? Of rho, of radial distance. You all see that? It's not a constant. So the further out you get, the smaller this gets. Do you all see that, class? And in the limit, if the B, the length of those plates went to infinity, it would go to 0. That's the reason you can't do that assumption where you assume charge and it's uniform. It's not on this one. Okay, so now to get the total charge, and I'll do it over here. I'm going to get Q, and I'm going to integrate, I guess I integrate over the lower plate. It really doesn't matter. But to get total Q right here, I'm going to say this is going to be an integral, that's a double integral actually, of that charge density minus epsilon V naught over alpha times 1 over rho. And now I need the differential surface of this plate. If you think about this plate into the board, like so, this is the Z direction, all right? And the differential surface here would be dz d rho. I hope you can all see that. Y'all follow me? Because V is held constant. So it's this surface right here. So I take this and I multiply it by d rho dz. Now, in that problem statement, he says that the depth into the board, or the depth along Z, is h. It's got a height of h, doesn't it? I think it does.
Yeah.
Right. So that means for the Z, it goes from 0 to h. Now, for rho, that goes from right here, from radius A out to radius B. Y'all follow me? That's where, because the surface is this lower plate right here. So I go from A to B, and really from 0 to h. When I do that, I get Q equal to, well, I can put the minus sign, epsilon V naught over alpha, comes out in front. Then I integrate dz, I get Z from 0 to h is just times h. And then I integrate 1 over rho, d rho, I get natural log. So then I have this times the natural log of B over A. Now something about capacitance is that the charge you use in capacitance calculation is strict positive. Capacitance is strict positive. Y'all follow me? So you find the charge on either plate. One is positive, the other is negative. This happens to be negative because it's the lower plate. And when I do this, I know that capacitance times voltage is Q, and therefore capacitance is Q over V. And this would be absolute values here. So if you look at this, I just get rid of V, and the capacitance should be epsilon over alpha times H times the natural log of B over A. Now the only thing you need to do is plug in the value of epsilon, which is what, 9 epsilon naught? Isn't that right?
Yes.
Yep.
All right, H, did they give you an H? I hope they did. No, so it's arbitrary. I figure if you're going to start nailing things down, you might as well nail them all. But that's the equation. You tell me what A and B are, tell me what H is, and tell me what epsilon, I can tell you the capacitance. That's pretty accurate too, but there's an assumption that they didn't say. When you talk about the difference in these radiuses, if you take a look at the ratio of B to A, it should be very large, over 100 for this formula to work. Because if you're talking about two plates out in the middle of nowhere, where the distance difference is very small between A and B, it doesn't work at all. But if you're talking about something where this is much, much, much closer than the outer one, where it looks like a hinge where you just basically whacked off that little bit there, then it will work. It'll be pretty accurate. Now, in the limit though, when these two plates are approaching, just think as A gets what? Bigger and bigger. Finally, when A is going to 0, the two short out, and that's where the failure is. You can't get them too close, or frankly, you'll get arcing right there. All right. Anyway, that's sort of a classic problem. It's more of a thing that gives you an idea of how the capacitance varies for these type of geometries, and I'll tell you where it's really useful. If you're trying to calculate the overall capacitance of an aircraft, knowing that helps, knowing that the way capacitance varies there and the way the D field does, it helps in some calculations. This is way down the line for what I'm talking about here, but there are reasons you need this. You need to know that. Okay, any other problem? Actually, I thought that was the trickiest of the problems I gave you, because you're unfamiliar with that geometry. I think Dr. Bashir likes that problem, and the students don't like that problem. Did you have problems like this in physics? That kind of problem or not? No. Usually they just like cylinders, they like spheres, they like planes. They don't like things that give it angles. And they don't like, I'll tell you the other thing that I give sometimes, I haven't given it here yet. I'll give two conic spherical sections. Now they don't like that at all. That's a del squared operator on spherical coordinates. And they'll boo me if I do that. But I sometimes, I'll show you how to do it sometimes. Right now, I'm not going to today. But later on, when we do some differential equation solutions, I will. Any other questions? Okay, I gave you quite a few capacitance problems. I'm going to ask you to do one with me, my problem for you, see how you do it. Now, all of you have had circuits, right?
Yep.
And somewhere along the line, Dave Irwin or whoever you had taught you that capacitors in parallel just add the capacitances, right? And resistors in parallel are basically one over the first plus 1 over the second, right? Resistance goes down, capacitance goes up for a given geometry. Keep that in mind when I'm asking you these things. So I'm going to give you a problem. I'm going to ask the class this, and it's going to be a sphere. Not your usual sphere. So it's got an inner radius A, that's fine. It's got an outer radius B, again, you're loving that. Seen that drawing before. But it's made of two different kinds of materials. And now I'm going to put a line down here. Remember, it's a sphere. And I'm going to say the material above here, above the plane, has a value epsilon relative 1. And below the plane, it's epsilon relative 2. So think of it as hemispheres, two exact hemispheres. North and south hemispheres, one with epsilon relative 1, one with epsilon relative 2. And what I want is the capacitance, effective capacitance between the inner radius A and the outer radius B. Now we did this one for a constant epsilon entire sphere, right? How would you do it? I'm asking you. There's a lot of ways to do this, bro, not just one. There's clever ways based on circuits, and then there's brute force ways by solving del squared equation. Either one will get you the solution, but one is a little more time consuming. How would you do it for a Jeopardy question with $1,000? Anybody got an idea? Your gut tells you something. It looks like two parallel capacitors, doesn't it?
Yeah.
Sure does. As a matter of fact, I could say if I had an entire sphere, this is just me, if I have a sphere of inner radius A, outer radius B, filled with the epsilon, there is a capacitance here, and that capacitance would be epsilon, right there, it would be epsilon relative to epsilon naught, right? And then if you think about the way we do this problem, well, I'm going to do it this way. For a spherical capacitor, if you assume Q, right, I'll do this quickly, you don't need to write this down. Q, you get D is equal to Q over 4 pi R squared AR. Then you get E is equal to D over epsilon. Then you get V by integrating E from A to B, taking a magnitude. So it's going to be Q over 4 pi R squared AR divided by epsilon dot AR dr, right there. And you end up getting Q over 4 pi epsilon, and then it's going to be right here, it'll be R minus R right there, but when you flip the limits, you get 1 over A minus 1 over B. I hope you appreciate I'm doing it fast. That's voltage. Then you find capacitance is Q over V, so it's 1 over that. So you get 4 pi epsilon divided by 1 over A minus 1 over B. And we did that. Remember that? That's capacitance of the whole sphere. I'm doing it quick just to show you how I would get it if I had to. Now, if you wanted to do this one, remember how before I just showed you a problem. If you try to assume Q here, you would be in error because you're going to find out that the charge density on one side is different than the other at that surface, all right? The only thing you could assume is the voltage V here. Just listen to me. The voltage V across this inner surface, because it's a perfect conductor at A, would be a constant. You could go that route. I'm just telling you, you could. I can do that. If you assume this is V naught and this is ground, then you could solve the del squared V equals 0 equation, and you could get an equation for the voltage versus radial distance. I want to talk myself through this kind of quick, and then show you the easy way to do it. Then after that, you could get the E field. Once you had the voltage as a function of R, you could get the E field by taking minus the gradient. You all with me? Once you had the E field, you could get D, correct class? D is epsilon E, and once you had D, D normal is rho S, so then you take rho S and you would integrate it over the surface, the inner surface. And rho S would be different on one side than it is on the other. And you can get the total charge, then you could say that C is equal to Q over V, and just telling you can do it that way. However, there's another way you can do this problem. And this is what I'm about to show you. Well, I'm going to say that if the total capacitance is that for this system, then I'm going to make the claim, you're going to have to take my word on this one, that for this problem, in the upper portion of this, there's really a capacitance of C over 2, and in the lower portion, there's a capacitance of C over 2. You all buy that? Think about the reasoning behind it. I can prove it, but it'll save me some time if I can establish that fact with you. You all believe me there? As a matter of fact, if you busted it into quarters, you could say quarter the capacitance is there of the system, quarter from here to here, quarter from here to, or any, as fine as you want to mesh that thing. Now, I broke it into hemispheres because technically speaking, you could get conic sections, which are a little different volumetrically than simply slices, all right? You all follow me on this, class? I'm not going to mess around with that. You're going to have to take my word on this part of it. Now, for this problem, do you agree if we could get the capacitance as if the whole thing was filled with epsilon relative 1, and then take half of it and say that's the capacitance from here to here? You all follow where I'm going? Then I'd make the claim that if the whole thing was filled with epsilon relative 2, I'd take half that capacitance from here to here. They are in parallel, so it added. Y'all follow me? I'm going to do. That's the easy way to do this problem. But I'll tell you, If I don't go through this, I will see the hard way being tried. Usually fumbled, but being tried. I'll do the hard way, but I'm just telling you the facts of life here. All right, so what is, if I wanted the capacitance of this, epsilon relative 1 above, epsilon relative 2 below, I'd say the total capacitance would be 1. Would be that capacitance up there divided by 2. You all see it up there? So it'd be 2 pi epsilon relative 1 over 1 over A minus 1 over B plus 2 pi epsilon relative 2 over 1 over A minus 1 over B. You all follow me on that? That's the total capacitance. That's an absolutely rigorous solution. I can prove that. And it's so much easier than the del squared business. I can do the del squared if you want me to. Y'all, go ahead.
Would you have epsilon naught too?
Well, epsilon, I should say epsilon relative to 1 epsilon naught. I should just say, I'm sorry about that. I should just say epsilon 1, epsilon 2. My bad, but that, you get the idea. Y'all follow me on that? Not done yet. Okay? Now, same exact geometry, I'm going to change something. Same exact geometry. Instead of epsilons, listen, sigma 1, sigma 2, and now I want the equivalent resistance between them. All right, I would want the resistance between inner and outer. Remember, resistances in parallel add as 1 over the first plus 1 over the second. You all with me on this? So how would you do that? And this is one of those problems, you can't just assume I on this one. What you unfortunately have to do is assume V, just like on the capacitance problem. And from V, you get E, from E, you get J. From J, then you integrate over the both surfaces to get the total I. You take V over I to get R. But how would you do this one based on what I just said? Think of the parallels. Well, do you remember that's capacitance for a sphere? Remember doing resistance for a sphere? No? You will. Whether you like it or not, you will. So if I have sigma here, inner radius A, outer radius B, and I want the equivalent resistance, R, right here. How do I get it? Remember how we did it before? I'll just go through it. We assume I, right? Then we get J is equal to I over 4 pi R squared, right? AR. Once I have J, J is sigma E, right? So I can get E by taking J over sigma, and then I get V is equal to, and I'm assuming sigma is a constant, it's going to be 1 over, or really it's I, here, let me do it this way. V would be the integral of I over 4 pi sigma R squared AR dot dr, AR. And we go from A to B, and sure enough, I have I over 4 pi sigma, and then it's going to be 1 over A minus 1 over B. Y'all follow me on this, guys? That's V, correct, class? And I know that R is what?
V over I.
V over I. Some of you are catching on why I'm doing this. So it's simply 1 over 4 pi sigma times 1 over A minus 1 over B. You all follow me? Remember doing this problem? All right, this is a classic problem. There's something about to show you that's really going to help you. But for now, you all agree with that, right? Now, do you all agree if the entire thing is filled with sigma, that would be the resistance, right? What if half of it? Wouldn't I say that if I only had half of this, then this would actually be 2R above and 2R below because they're in parallel. Do you all agree with that? How many see this right here? So resistance goes up for half of it, right? Okay. So if I wanted the resistance between the inner and lower, or the up, between, sorry, the resistance between A and B for this system, I could say R total would be equal to the resistance as if half of the thing, or the whole thing was filled with material sigma 1 times 2. Y'all follow me on this? Because it's going to go up. So I take that equation times 2, and I get 1 over 2 pi sigma 1 times 1 over A minus 1 over B plus 1 over 2 pi sigma 2 times 1 over A minus 1 over B. Are you all with me on that? With resistances, the smaller, I mean, when you take half of the volume on a spherical problem, it's twice the resistance, because when they're in parallel, it's just R, okay? This is important. You all see the principle I'm showing. And here's one other thing that's very important for you to see, and some of you do. Let me get rid of this stuff, the clutter. This always is good. So if you have a system like I have here, and you have an inner radius A and an outer radius B, and it is filled with a material sigma and a material epsilon. So it's a constant value, both sigma and epsilon in this material, okay? That means there is an effective capacitance from here to here and an effective resistance from the inner and out. You all with me in this class? And this is real important you're listening. Now, because the materials do not change versus any spatial position, this is real important, then I can say that R, the equivalent R from here to here, times C is equal to simply epsilon over sigma. Now this is really, really useful. You know why? Because I knew capacitance right there, right? If I wanted resistance, I just take 1 over this value and multiply by that term. Y'all follow me on this? Now, how many can see it works? If I want resistance, it's equal to epsilon over sigma, right? Times 1 over the capacitance. Take 1 over that, right? And I think you can see it. So I get 4 pi epsilon times epsilon. Epsilon goes away. Divide by sigma, so it's 4 pi sigma. And then, what do I get? 1 over that would be 1 over A minus 1 over B. Y'all see that? Now that's real handy, because, and that will work for cylindrical systems or planar systems, as long as the material in between the business is constant, the sigma and epsilon. One last thing about these problems, because I do this, and I know how important it is. What if I have this system? I'm going to stick with epsilon for this one, so, well, let me make it bigger. All right, I got a spherical surface like this, inner radius A, outer radius B, all right? But now things change. Now I'm going to separate this further. And I'm going to say from A, I'll change this, and I'll make this A1. I'll have a material epsilon relative 1. And from A1 to B, I'll have epsilon relative 2. So now I have 2 concentric spheres, one with a given, with a permittivity epsilon relative 1, and one with a permittivity epsilon relative 2. I'm going to ask you to do the capacitance calculation for this. So I want to know what the net capacitance is between the inner and outer radius. How would you do that based on what we just talked about? Well, I just want to say, you can assume a charge density. Guaranteed, Q in the you could put Q on the inside, get D is Q over 4 pi r squared. Then you could get the E field. You would have a different E field here than you would here, because 2 different epsilons. You all with me? Then you would have to integrate the E field from the inner to the outer to get the voltage, and that will work. It's not that bad, this one, is it? What would be an easier way? Doesn't it look like a capacitance from here to here, y'all follow me? In series with a capacitance from here to here. Y'all see that, class? So you could say you have a spherical capacitor, inner radius A, outer radius A1, filled with whatever epsilon relative 1. Calculate that capacitance and add it in series to a capacitance over here that would be, now have B and A1 as the outer and inner radius filled with epsilon relative 2, and they would be in series, which means the final capacitance is 1 over the first plus 1 over the second. Y'all follow me? And I can partition that to as many concentric spherical surfaces as I want. It's real important to appreciate this works for cylindrical systems, it works for planar systems. You gotta define if it's in series or parallel. And the whole deal with series and parallel, with resistances, you got a real good feel for that, right? For series resistances, the same current has to go through every resistance if they're in series, right? If they're in parallel, the same voltage has to be across each resistor. For capacitors, same way. That's how you can figure out if they're in series or parallel, if there's ever a problem. There usually isn't. You with me, class? I hope what I showed you helps you. I really do, because this stuff here is not really, Dr. Wentworth's book doesn't bring this out the way I like to see it brought out, because this is basic application stuff. Now, the next chapter, we didn't talk about energy, but you know, capacitance energy is what? If I ask for the energy in a capacitor with a given voltage across it, remember? If you have a given capacitor and I put a voltage plus the minus V naught across it, and this is a capacitance C, then the total energy is 1/2 CV squared. Y'all remember that, class? You gotta know that. All right, make sure you do. And now, the last thing, well, the one thing I'm gonna leave you with, because we're coming into Friday's lecture, the quiz will be on capacitance, resistance kind of problems. Got me on that? Relationships of that. And you may have to do a calculation, one or the other, that involves actually assuming Q and going through the whole thing to get DE and then V. But next thing I want to tell you is we're going to be talking about magnetics, magnetostatics. Now, magnetic stuff is, in my opinion, a little more difficult because of only one fact, and that is the relationship to the field, to the actual field quantity H and the thing causing it Q. They're perpendicular to one another, and I'm going to have to show you. If you have a current I1 here, and it's got a length DL, so that's a differential vector length, DL. And I come out at any distance R away, and I want to know what the differential H field is out at this point. Now, listen to me on this one. That differential H field isn't in the direction of R. It's perpendicular. And this differential H field here is equal to I1, that's the current causing it, DL. Now that's a vector right there, DL. And it's crossed into a unit vector AR, coming from that region to this region. I just call it AR because AR always, in my opinion, points from the source of the field quantity to the point of observation of the field quantity. Points from here to here. So that's the direction of AR. It's a unit vector. It's over 4 pi R squared. And here, this is R right there. R is a vector. Now, this is the thing different. Remember when you had the differential, say, D field, or it could be E, but yeah, I'll do differential E field. That was Q, or dQ, over 4 pi epsilon naught, R squared AR, right? And the electric field was along the vector direction. It was in that direction. You all remember that, class? This one says it's not. It's actually, to get the vector direction of H, I have to take VL, and I have to cross it into AR. So in this case, if I was in the board, and R was in the plane of the board, when I take IDL crossed R, it would be into the board. How many remember the right-hand rule? Anybody for crossing vectors? Do you remember doing cross products of vectors somewhere? Did you have it in math or not?
Yes.
Okay, I think you did, but you may not remember it. So if you have a vector A, and it's crossed into B to get C. The way people normally teach this is if you have a vector A and a vector B, and I'm going to just connect them like that. When I take A cross B, I take my right hand, assuming you have one. Take your index finger on your right hand, put it in the direction of the first vector. This is called the right hand rule for crossing. In the direction of the first vector, and then use your thumb as the hinge to go through the smallest angle into the second vector. Your thumb will point in the direction of the cross product between A and B. You'll notice my thumb's pointing into the board. You all see that? So it doesn't matter the coordinate system's used, that's the way you can get a visual on what's going on. So for this one, I got IDL going that way, crossed into AR, that way, it's going into the board. H is going, or the DH is going into the board. Hard for me to draw that, but I hope you can appreciate it. That's real important to understand. Now, I'm going to go through on Friday some calculations of basically the H field from infinite lines, like we did for constant charge density. You're going to have an infinite line current, calculate the H field. I'm going to have a loop of current, calculate the H field on the Z-axis, and do some of the classic problems before you leave for spring break. I want to get that underway because after spring break, we got to cover through chapter 4 and 5, and that can be a little much without me at least getting started. Any questions? All right. So when you show up for Friday, please come with the charge battery calculator and stuff like this. The quiz will be at the end. It's going to be related to the homework material for today and Friday that I'm going to give, and some of the past stuff that deals with resistances. All right, so you're going to get something that is going to be a resistance capacitance kind of question. You got to calculate. Got me on that class? All right. I'll see you Friday. You got questions?